Four properties of waves that are exhibited by EMR. One is refraction, which we've been talking about quite a bit lately, right? Refraction, the bending of a wave, exhibited by EMR. EMR must be a wave. One was polarization. Polarization means the filtering out of certain components. One was interference, which we're going to talk about in a few minutes, actually. The other one was diffraction. Diffraction, if you remember, was the spreading out of a wave around a barrier or an opening. I can draw that out like this, but I got a better real photograph of diffraction taking place there. Wave goes through like this. What happens when it gets to the other side? It spreads out. Okay, it happens in real life too, not just in theory. The spreading out of a wave around a barrier or through an opening. The diagram you see up on the board is called interference. The diagram here is formed when you have, the guy has two tennis balls actually. Two tennis balls, okay, and he's bouncing them up and down in the water producing waves. You can see the first one is producing a circular wave, so is the second one. But those two circular waves, it's the equivalent of diffraction, right? They interfere with each other, produce bigger waves and smaller waves. You can see actually that when the EMR constructively interferes, so crest meets a crest or trough meets a trough, we get this whole line of constructive interference. We get another one right here. We get another one right here. We get another one right here. We get another one right here, and so on. We get these alternating lines of constructive interference. But in between, you can see that we get these areas of destructive interference. That's not very good. Let's change that color. That's still not very good. I don't want to make that a bright color is the thing. Let's make it green, yeah. Destructive interference, destructive interference, destructive, and destructive interference. Now, these are water waves. You can clearly see the areas of constructive and destructive interference, right? You can see the light reflecting off of the big waves and then light reflecting off of the no waves where light has destructive, or where the wave has destructively interfered. But if this is light waves, visible light, let's say, we're not going to see this. Okay, we don't see this because there's nothing for the light to reflect off of. So what's happening, you're getting these lines of constructive and destructive interference, but we don't see it. In order to see the interference taking place with visible light, we have to put a screen up here. A screen, like maybe it's a piece of cardboard or a wall or a piece of paper. On that screen, you would see a bright spot right here. You would see a red dot right here corresponding to the constructive interference. You would see right next to it what? A dark spot, or might be more appropriately called an absence of light or an absence of bright spot. Because it's not like it makes it dark, it's just that there's no light there. We call it a dark spot, but really it's just the absence of light. So bright spot, then nothing, and then light, bright spot, and then nothing, and then bright spot again. Same thing on the other side. Bright spot, dark spot, bright spot, dark spot, and so on. Now, just remember, this interference is taking place, like the pattern that you see with the water here is taking place with the EMR, the visible light as well. It's just that we can't see it like we can with the water waves until we put the screen in there to detect it. Make sense? Now, you could, I suppose, put some kind of like, I don't know, fog in here or something and see some of this, right? But normally, because there's nothing to reflect off of, you're not going to see there. Sorry? All right. This diagram we see right now is just an idealized version of the diagram we just drew, right? We got the light waves coming down here, red light waves. It's diffracting. You can see the circular pattern formed there. And then, of course, it's interfering in the middle. And then it's producing areas of constructive and destructive interference, alternating. The dark ones are the constructive, the white ones are the destructive. And then, of course, we don't see that because it's light. Where do we see it? Oh, on the screen down here. Okay, down here, where we see bright spot, dark spot, and so on. This one, that middle one, we usually call the central maximum. And we call it the central because it's in the middle. Maximum because it's maximum brightness. Sometimes we call it the central bright spot. Sometimes we call it the central area of constructive interference. As opposed to this one, which we would call, another name for it, maximum bright spot, constructive interference, antinode, versus the one next to it, which would be, not the node, no. This would be the first order, maximum, bright spot, the first order constructive interference, the first order antinode. By the way, this is the first order, but so is this one. On the other side of the central maximum, they're both called first order. These ones right here, we would call the second order maxima, right? Second order maximum, second order bright spot, second order antinode, second order area of constructive interference. What do you think we call these dark spots in the middle here? This one and this one. It wouldn't be central anything, because the only thing that's in the middle is this one central maximum. These would both be called the first order minimum. Along with the first order minimum, we call it the first order dark spot, the first order destructive interference, the first order node. All of them mean exactly the same thing. So be prepared for all of those terms. So this diagram that you see up on the board now is a graph. This is the last thing I want to do here. This is a graph that shows intensity versus position. If I was to create this interference pattern on a screen, let's say up here, and then I would get an interference pattern that showed bright spot, dark spot, bright spot, dark spot, and so on. Take a look at the graph now. What is this graph showing us? Well, in the middle, where we have our central maximum, by the way, our central maximum, we often assign a number of 0 to, central maximum, or n is equal to 0. Our central maximum is the brightest spot, hence the intensity is highest. What do you see right beside that central bright spot? Dark spot, where the intensity is 0, or lowest. What do you see right beside that? A bright spot. It's not quite as bright as the first spot, right? It's the central maximum. The first order maximum, though, is bright compared to the minimum. Then there's the minimum, where there's 0 intensity. Then there's the maximum, again, the second order maximum. And again, the same thing on the other side as well. Central maximum, first order, second order. Yeah. As you get further away, we would say that you don't get that clear distinction between the bright spot and the dark spot. So that's why you're seeing a little bit of for all intents and purposes, there's still no light here, right? But if you're measuring with a sensitive device, you might find some intensity there, just not anywhere close to what we see here. Does that make sense?